What makes a rational, thank you, a rational function a rational function? There are x's, that's good. X is on the top and x is on the bottom, which means there is a top, there is a bottom, there's a fraction, right? So a rational function, there's a top, there's a bottom, a numerator, denominator, and we have x's all over the place. In your 2-6 homework, there are going to come problems that basically kind of have like a, hey, find this and this and this and this and this and this and this. And you're like, yay, thanks. And then sketch at the end. That's what I'm modeling, okay? So let's go ahead and let's make sure our notes are open. I'm doing this for you. Don't make me regret it by wasting your time. Have notes open, and let's go ahead and get one last big example, big recap of all of section 2.6 done, and let's keep going. So, why is it telling me to factor? Holes and vertical asymptotes. We're trying to see what's going on in those denominators. So, if we factor the top, hopefully, you guys haven't been this removed from that. What's the factoring of x squared minus 4? Good. X plus 2, x minus 2. Look, no number in front. Whew, could have been worse. What's the factoring of x squared minus 3x plus 2? Good. X minus. We could have done x minus 2, x minus 1, or x minus 1, x minus 2. Either way. Now, what do you see with those factors? You can reduce out x minus 2. There's a shared factor at 2. And we could rewrite this and say, okay, so it's x plus 2 over x minus 1, but x cannot equal 2, right? Have to maintain that restricted domain. And technically, what's going on? Because we were able to remove it, exactly. We have a hole, and technically, we could be amazing, and we could not only say there is a hole, we could say the exact location of the hole, because once you remove the hole, you figure out the rest of the function without it. AKA, we can say there's a hole at 2 is our x. We can't find our y from this one, because that would be 0 over 0. That's not getting us anywhere. But what if we plug in 2 to this one? Does that give us a number? Yeah. And 2 plus 2 is 4. And 2 minus 1 is? So 4 over 1 is? Sweet. I know one placement. I know one piece. And technically, by looking at this, I'm going to skip just a little bit, can't we also answer the vertical asymptote question? We'll get back to that in a second. Okay, y-intercept. Now what? Y-intercept, we set the x equal to 0. Remember, y-intercept, we want, at the end of the day, we want the y or we want the b. You think about it that way for mx plus b if this was a line, which is not. But we set x equal to 0. So we can take our little equation. Now guys, we could take this one, but that plugging in doesn't look as nice as that plugging in, right? So let's just keep working with the easier function the rest of the time. Makes life easier. So we can say y is equal to 0 plus 2 over 0 minus 1. We can always work with that easier function unless we're at the 2, and that's that one place where it doesn't work, but we already wrote that down. What happens when we plug in 0? What do we get? Good. A positive 2 over a negative 1, which is a negative 2. So far I have a hole. So far I have a point. Let's keep going. X-intercept. Now what? Set the... Good. The other one. Set the y equal to 0. Now this one gets a little tricky. This one gets a little tricky. But we can still take the easier function. Set the y equal to 0. How do we solve? Multiply that denominator over. Now what's weird though about multiplying that denominator? What happens when we multiply it by 0? Yeah. So in essence, this one, by multiplying by x minus 1, by multiplying by x minus 1, whenever we're looking at the zeros of a fraction, we're really just looking at the top because the bottom will always disappear. And we end up with, oh, that's weird. X equals? Huh. All right. We have 0, negative 2, and we have negative 2, 0. We can do that. Now, just a second ago, I said, hey, we can see the vertical asymptote. Let's get back to that, because here we are at the vertical asymptote step. Vertical asymptote at x equals, where is that other discontinuity? What x value would make the whole function undefined, but was non-removable? Good. You come back and say, who's left? X minus 1. And who's what? Who or what is the 0 of x minus 1? 1. Sweet. So that's my vertical asymptote. At x equals 1. Technically, the domain would say x cannot equal 1, but since we're stating where the vertical asymptote is, that's all right. How do we do horizontal asymptote again? The degree of the leading term. We can say that. The degree of the leading terms. And I see top wins, bottom wins, or ties? Ties. Now, someone did say leading coefficient, and why is that going to be helpful? What do we do if there's a tie? Leading coefficient of the top over leading coefficient of the bottom. And as I look at the leading coefficients, it's 1 over 1, right? So where's my horizontal asymptote? Now, who or what equals 1? Nice. It's horizontal, right? Vertical, it's x equals. Horizontal, it's y equals.
I have a question on the factor. Why can't x equal 2?
Just looking at this, it's okay for x to equal 2, but we have to remember where this came from. So this entire page is supposed to be describing this function. I can rewrite this one as a simpler, but when I cancel out, I have to say, uh-oh, but in the original, it wasn't allowed. Does that make sense, Anna? Okay. So I'm writing it in order to say, ooh, yeah, that's right. You don't see him, but he was there. Okay, now, your book is going to say something like, and technically, I don't think it says sign chart. Your book is going to say something like, sketch, what is it? Yeah, something about extra solution points, as many as necessary or something like that. When they say sketch extra solution points, I'm not saying you can't, and actually it's not a bad idea. But for rational functions, I'm saying you don't have to. We called it a sign chart back in the day because we would set up a little baby number line, put all the important stuff, and then choose little places, little points in between there. But I'm going to actually change this step, and so when you get to it in homework, change this step. You don't have to make a table of all these extra points, just so you can if you need a little bit more guidance on how to sketch. But I'm going to say just check the behavior near the vertical asymptotes. And I'm going to show you why, then we're going to come back and do that step. So skip a couple lines. Let's say actually skip 2 should be enough. 2 should be enough. And let's go ahead and put together the pieces that we have first of all, because at the end of the day, we just want a really good sketch of this function. So we're going to come back to this last point, to this last step in just a second. What do we know? All right, we know there's a hole. Where? Okay, at 1, 2, 1, 2, 3, 4. What else do we know? 0, negative 2. Negative 2, 0. What else do we know? What else do we know? Sorry, apologies for that. Could you make an educated guess as to what this graph looks like? Let me guess your educated guess. Something like this, and something like... How many of you guys would have educated guessed that? Okay, pretty good. A few others. Do you see why they're guessing that? This one, you can kind of see it going down. You're like, oh, hey, it has to get closer to the vertical asymptote. And it has to get closer to the horizontal asymptote. And you might see this piece and be like, whatever, this is the other one. But let me, just as a warning, not for this function, but I'm trying to show you a possible graph, because I've seen some really nasty ones in my day. Usually more in calculus. But, believe it or not, something could actually Now this begs the question, exactly like Caleb was asking. It goes through the horizontal asymptote that's not allowed. Vertical asymptotes come from domain restrictions. Vertical asymptotes come from places where the function cannot exist, possibly cannot be there. Vertical asymptotes. Horizontal asymptotes just come from, hey, what's going on over here, guys? And they're getting closer and closer to a number. Functions actually can cross horizontal asymptotes. But at the ends, they still have to be getting closer and closer. Vertical asymptotes are the ones where a function is not allowed to be ever at that place. Now, I'm not saying this function is this, but question. What is one clue, one hint, one test we could do that would show us the difference between this one and the one you guys thought of? For mine, as I come from the left, where's the function, the left of the vertical asymptote? As I come from the left, where's my function going? But with yours, where was it going? Oh, so if we just figure out the behavior near the vertical asymptote, we'll figure out which one's which. Kind of makes sense? Now remember, we're in Precalc. We're not trying to get perfect graphs. We're trying to get really, really, really good sketches, good ideas. They don't have to be perfect with every single important point marked, but we do want to have a really, really, really good idea. We just saw, there are nasty things out there lurking in the shadows of your math textbooks. So, let's check the behavior. I'm not going to make you do, because you guys got a really good sketch, and to be honest, it's the right one for this one. You got a really good sketch without making this whole extra table that the book makes you do. So I don't think you need that, but I do want you to check the behavior near the vertical asymptotes. And in case you guys have been on retreat, or at least you haven't been in my classroom, most of you, for a while, in case you forget what this means, what this looks like, let me write something and see if it jogs your memory just a little bit. I'm going to write as x approaches. Who's my vertical asymptote? 1. F of x approaches. Oh, but wait a minute. Can't you approach from 2 different sides? You guys remember how we show the difference? Because right now it looks like the exact same thing. A little minus to say from the, that's supposed to be in the exponent. When there's a minus, you guys remember what way we're coming from? The left, from the lower side. And the little plus means we're coming from the right. Now, do you remember the 2 answer choices for each one? The y's are either going up to infinity or going down to negative infinity. How do we tell the difference? Plug the function into our calculator, go to our table, 2.9, 0.99, 0.999. No. Plug it in, not just the denominator though. Plug in a test point. Do you remember that? And we just need to check the sign. I'm going to zoom in down here on this bottom, if I can. Will it let me? Oh, it doesn't let me. We don't need to be sketching right this second, so let me go back to single page and then let me zoom in. Quick reminder, remember, this is one huge recap of section 2.6. In order to answer both of these questions, we can take our original function. Oh, he was gross. Let's take the easier function. Y equals, what did we have up top once we canceled out that common factor? X plus 2 over x. Why did I leave the x spot blank? I'm going to plug something in just so. Okay? Now, think about a number line. If I have 1, what's something zoomed in really close, but on the left of 1? 0.9. Let's plug them in. Alright, cool kids? Just check the sign. 0.9 plus 2, 0.99 plus 2, 0.999 plus 2. What's the sign? Positive. I have a positive up top. Over 0.9 minus 1, 0.99 minus 1, 0.999 minus 1. Exactly. And what's a positive over a negative? So what am I going to answer for where my y's are going? Booyah, I didn't have to go to my calculator. Didn't have to. Yeah, there we go. At least we have the terminology right. Okay, so then y equals somebody plus 2 over somebody or something. Maybe I should practice on finding my numbers. What can I plug in that's really close to 1 but on the right hand side?
1.00001.
Go for it. You want 1.00001? I don't have that much room. I'll do 1.01. How about that? 1.01 plus 2, 1.001 plus 2, 1.0000001 plus 2. All of them have the sign of? Nice. 1.01 minus 1, 1.001 minus 1. All positive. What's a positive over a positive? So what am I going to fill in as where my y's are going? Ooh, yeah. So how can you justify your graph on the other page that you, a lot of you, naturally thought was the right one? We add one more clue. And we say, hey, as you come towards the vertical asymptote, you better be going down, and you better be going up. Well, in that case, the best sketch that you can make at this level with the information you know is the following. Now, some of you might be like, but can't you still dip down? And yeah, you can. But I'm just saying, remember, we're just trying to get a good sketch. The best sketch we can with our pre-cal knowledge. So we're just going to make the simplest deduction. Ricky, go
Why
ahead.
does it look really weird when you plug it in?
What do you mean?
I plugged it in, it doesn't really look like that. I don't know if I plugged it in wrong.
Kind of. Did you put parentheses around your numerator and denominator?
Or around my denominator.
Not your numerator, though?
No.
Better do that. While I get that up to double check for Ricky, I want you guys to go ahead and we're just going to do a quick recap. We're just going to do a quick recap of 2-6. Oh no, it's in the way. Hold on. See if that little calculator can get out of there. He's in the way. There you go. Just get me one line for each. That's all we need. Just one line for each.
Is this notes?
Yeah, the very last part of 2-6. I'm getting the graph for Ricky. You guys are doing notes.
So leave a space for each one.
Yeah, one line for each one. Ricky, did you do the whole thing or did you do the,
I got it now. I don't putting parentheses in the numerator.
oh, yeah.
But,
Because otherwise it just divides that last piece you put and then it messes everything up. All right, then we'll go ahead and leave the graph off. It ends up looking like what we have. And I think is it zoom decimal where if you zoom in you can see the whole, isn't that it?
Bless you.
Okay, this is just so that you guys know how to read the directions, okay? When it says simplify or factor and simplify, well, I just gave it away. What are you supposed to be doing? Factor and reduce. I'm going to say reduce if possible. Why? Does a function have to have a hole? No, it doesn't have to have a hole. So maybe you can't reduce. But you can still factor. You should still factor. Find, plot the y-intercept. Quick review. What did we set equal to 0 for that?
Oh, wait. X's.
Good. Set x equal to 0. Solve for y. Remember the y-intercept is 0, comma, b. If that helps. In case you're wondering what this little random line is when we're given a rational function, f of x over g of x. That's who we're dealing with. Find, plot the x-intercepts. Set the other one equal to 0. Set y equal to 0. Solve for a. Number 4, find/sketch the vertical asymptotes. I'm just going to say at x equals, and it's from the remaining factors in the denominator. Remaining, what? Oh, the ones that didn't reduce away. So any remaining factors in the denominator, the ones that didn't reduce away. Because the ones that reduce away are wholes, remember? Find, sketch, horizontal asymptotes. Remember what we did? Review. Look at the degrees. Good, degree test. The degree test. Do you guys have all those details in your notes? Good. So the top ones, he's going, nothing's holding him back. He's going either to infinity or negative infinity, no big deal. The bottom ones, the top is being pulled down all the way to zero, is being held back. And if they tie, it's just the ratio of leading coefficients. The degree test of top and bottom. Now, number 6, find plot test points. At least one. Oh, what? You have to make a table? What did I say instead? Okay. Now, why did I still put this? Because the book is still going to say this. It's going to say find sufficient solution points, plot more points. What did I tell you to check instead? Behavior near asymptote days. The DAs. If you need a quick help, a quick reminder. Remember, as x approaches, I'm just going to say C, because we haven't used C in the page yet, so it's as x approaches wherever the vertical asymptote is. From the left, trying to fill in the blank. And then as x approaches C from the right, try to fill in the blank, and you guys have that example we just did to help. And then, do the best you can. Connecting with smooth curves. Coming in towards the vertical asymptotes if there are any, however you need to. And then somehow approaching the horizontal asymptotes as you go to the right and to the left. Done. Now, this was a great recap of everything in section 2.6 except the one asymptote day that we didn't cover because our function didn't have it. The slanty one, the oblique one. Struggle, the slanty one, the oblique one. Uh-oh. Why didn't this function have it? Couldn't he have had it? Shouldn't we have checked? It's when the degree of the numerator is 1 more than the degree of the denominator. If we had an x cubed over an x squared, then we would have had to find a slanty asymptote. However, another reminder is if you have a horizontal asymptote, that's what's going on at the ends. You don't have to check for a slanty one. If there is a horizontal, there is no slanted. And if there is no horizontal, check for a slanted or an oblique. It will only happen when the top is 1 higher than. And can you guys remember how we find the slanty one? If the top is 1 higher, or the degree is 1 more than the bottom. Long division. Remember? The quick recap. Long division. You divide the top by the bottom. I think I have them here pretty closely. Divide the top by the bottom. There's going to be a remainder. You ignore the remainder. The only time the remainder would be 0 is if you forgot somebody when you were factoring. So there is no remainder. And you just keep whatever is left. It should be linear. Y equals, and that is the oblique asymptote. And when we graphed it, remember it was really weird. Because you had your graph. You had your y equals x. And I think you had a vertical asymptote at 1. Something like that. And then your function was funny because it was like going towards the vertical asymptote, but it was also going towards the slanty one. It was going towards the vertical asymptote, and it was also going towards the slanty one. So that's what you do with slanty. All right, 2.6 done. 2.7, let's get into it. Good job, guys. Way to hang in there, and I hope that helps for those of you guys that still need to finish 2.6 tonight. If you need to finish 2.6 tonight, we just did one big recap and really one problem. Intense, but hopefully helpful. All right, 2.7, the final section of chapter 2. Nice thing is, there were 10 whole sections in chapter 1. There are only 7 in chapter 2 to focus in on.
Cool, so we're going to have Thursday and Friday to like review kind of.
Friday and Monday.
Friday and Monday.
Yeah. We'll still be working on 2.7 tomorrow.
Oh, okay.
Now you've seen the words sign chart a couple times now. And this is the only section where we're truly going to actually deal with the signs in the charts. But the nice thing is, hopefully you guys at least somewhat have in the back of your mind somewhere sign chart. Oh, number line. Hopefully you kind of have that one down. And if not, it's okay, we'll review it. But sign charts, oh, number line. That's all we're worried about. And as you guys can tell, inequalities are coming. What are some inequalities that are out there? Greater than? Less than? Greater than or equal to? Less than or equal to? And technically, I guess we could say not equal to, but that we don't generally describe as an inequality. As kind of an introduction to this idea and why we need it. Let me start off and let you guys have a little bit more time as you're writing. What's the first example we come to? Struggle. I'm just putting on the board an example that's coming. Was less than or equal to 0. Why is this so hard? Why does it have its own section? Well, half a section. Half a section is on like quadratics and inequalities, and the second half of the section is on or in or with rationals, meaning fractions. But we start off just with polynomials, non-linear, so it can't just be an x to the first power. Why is this hard? How do you get x by itself?
Factor.
Okay. So if we did factor, some of you would say add 6 to the other side. That is horribly wrong. Stop doing that. But factoring was a good idea. But what's the dilemma with factoring now? Oh, so he's less than 0 and he's less than 0. Done. Wait. Less than 0 means negative, right? If he's negative and he's negative, then this whole thing is a positive, and a positive is not less than or equal to 0. That doesn't work. Okay, no, it doesn't work. So, how do we solve that with this? We start with key numbers. We say that a polynomial can only change sign, positive, negative, negative, positive, at its zeros, so we start with key numbers. And what I mean by starting at key numbers is you do factor, and that's great, but you don't find the answer just by staring at it all day or just by making these random conclusions like, oh, they must both be negative, less than or equal to 0. It doesn't work. So instead with the key numbers. Now guys, for a quadratic, the key numbers are just the zeros. For a rational function, the key numbers are a little bit different. For a quadratic, the key numbers are just the zeros. You're going to see that in just a second as we keep going on here. So the key numbers would be positive 3 and negative 2 for that example. But for rational inequalities, what do you guys see that's different with that? A rational function can change signs at its zeros, good, or its undefined points. Stink. At its zeros, good, or its undefined points. Now, Here's a shortcut for how to find the key numbers. If you can get a rational inequality in one nice fraction, one put together fraction, not fractions on either side, not numbers on one side, fractions on the other, but if you can get everything on one side with the 0 on the other, we can just say the zeros are found by setting the top, make a little pitchfork. The zeros are found by setting the top equal to 0, like we saw kind of when we were finding the x-intercept on the page before. And the undefined points are found by setting the bottom equal to 0. That's kind of a shortcut if you can get everything put together, one nice fraction on one side with a 0 on the other side of the greater than, less than, greater than or equal to, less than or equal to. But either way, whether you have a rational function, one with a fraction, whether you have some sort of polynomial, polynomials, you want to find just the zeros. No big deal. All the solutions of a polynomial, factor and set equal to 0. For rational functions, zeros and undefined points. And then what do? Struggle. Here's our steps to solving. Whatever we have, whether it's a polynomial of a certain degree, or whether it's a rational, with a top and a bottom. For a polynomial, we just take the zeros. We factor and we find the zeros. For rational, we have to take the zeros or the undefined. Just quick reminder from the pages before. You take the key numbers and mark the intervals in a sign chart. Sign chart meaning just a number line. You pick a test value from each interval that the numbers in the sign chart split the number line into. And you just test true or false. And I'm going to say in a table. Now pencils down. Just to help you guys, I want to just quickly solve this problem. And I don't want to mess up your notes and make you guys skip lines or anything, okay? So, here's this one that we saw a second ago. You guys said factor and you were right on, but you weren't right on for solving, you were right on for finding the key numbers. I have x minus 3, x plus 2. To find the zeros, I can say x equals negative 2 and 3. I put them in a sign chart, negative 2 and 3. I make a table, and I'm asking myself the question, with test values, true or false? I pick one from this side, like negative 3. I pick one from in between, I don't know, like 0. And I pick one from over here, like 4. And I plug. I plug in where? Give me 10 seconds. Up here, or here. And I say test. And it might be easier to plug in like here. But long story short, you end up with this one being a false, this one being a true, and this one being a false. And guess what my answer then is? This one marks 2. Hey, everybody here, but not or equal to, not him, not him. My final answer, x is within negative 2. Get out of here, cool kids. Finish Q6 tonight. Thank you for your extra grace and extra seconds. Just a few of you might want to get ahead and start Q7. See you guys later.
Stop cyberbullying. You're cyberbullying.
Oh, my cyberbullying you.
Hi, Bennett.
Real life bullying. There's a difference.
Bye, guys.